construct a thing which I kind of announced and used, namely the non-commutative version of the Cartier isomorphism. So to remind you, sort of my goal is the following. I have some algebra A, have Hochschild homology of A iterated many times, and I have a periodic cyclic homology of A. And what I want to do, I want to construct a map, canonical factorial map. Well, unfortunately, not quite from this thing, but from some sort of additional functor applied to this, which I will also define today. So this is my goal. And the understanding is that this comes from some equivalence of spectra, but I will try to keep the sort of algebraic topology part to the minimum and stick to the things that we all feel comfortable about, or at least I do. So this is my goal for today. And to begin with, I will now give you the definition of the cyclic homology, which I didn't really do last time. As I said, there are different ways to do it. Maybe not all of them quite satisfactory, but the one that I will use has been invented by Kohn and uses the technique of the homology of small categories. It's really a very, very simple thing. So assume we have some small category gamma. Formally small means that the objects and the morphisms form a set, but you really should think of it as some kind of combinatorial data. Our categories will be really very, very small. And we can consider, so we fix a field K. And just once and for all, so it's perfect field of characteristic P. Although this is not important at this point. We can consider the category of functors from gamma to vector spaces. This is an abelian category. And we have so we have a category of just vector spaces. We have a sort of a tautological pullback functor which associates to any vector space just the constant functor, which sends everything in gamma to this fixed vector space. And there are two adjoints. So let me call it tau upper star, and this is tau low star, and tau low shriek. So this notation is chosen so as to remind you the maybe familiar things about Grothendieck topologies and things like this. But maybe even more, even simpler association to this is an example where gamma is just a category with one object, and all morphisms are isomorphisms. So this is essentially given by a group, J group. In this case, this functor category is just a category of representations of the group. And then these two functors are invariants and co-invariants. So this is the invariant functor of invariance, and then these are co-invariants with respect to the group. Now, as usually, so this functor is exact on the left, so you can take the right derived, and this functor is exact on the right, so you can take the left derived functors. And this gives you group homology. This gives you group cohomology. And this generalizes just tautologically to this more general setting. So this functor is exact on the left, so you can take the left, exact on the left, so you can take the right derived functor. And this is called the cohomology of category gamma of some coefficient some functor. And conversely, this is exact on the right, so you can take the left derived functors, and this gives you homology. So my definition of cyclic homology will be homology of some category of coefficients and some functor. So let me define you the category. This is a category introduced by Kohn. It's a rather simple one. So objects are just positive integers. I will denote them as n in brackets, where n is a positive integer. And one thinks of an object here as a circle with n marked points. And now if you want to define maps between two such things, we just consider maps from a circle to itself. Such that pi is degree 1, there is no winding. Sends marked points to marked points. And we require this is non-decreasing in the sense of a cyclic order. This means that 2 points can come together, but things like this are prohibited, so it cannot go backwards. And then we just take the homotopy class of these maps. So this is a finite set for any 2n and m, and there is an alternative definition of this category which is purely combinatorial, but this is maybe easier to visualize. And this category is almost the same as the category of finite cyclically ordered sets, and sometimes in literature you can find this as a definition. This is not quite correct, because if we have sort of a wheel with 2 marked points and another one with 1 marked point, then there are 2 maps in this direction, because both points, of course, go to this point. But you can choose which of the edges you contract. Either you can contract this one or this one. So there are 2 maps in this direction. And conversely, there are 2 maps in the other direction. Here, there is no choice about the circle, but the point can go either here or here. So this is our category lambda. Now, if we're given some associative algebra over K, then one can construct a canonical functor from lambda to vector spaces, which is denoted by a hash. And the definition is like this. So first of all, its values on objects are just tensor powers of a. So for a wheel with n marked points, we get nth tensor power of a. Just tensor power is a vector space over the base field. As for maps, well, I could write it down, but it's probably easier to tell this geometrically. So whenever we think of the factors in this product as being numbered by marked points. So whenever some marked points come together, like for instance these 3 points go here, then the corresponding map just has a multiplication at these positions. So just an example. So 1, 2, 3, 4, 5, 6. So a typical element in a hash of this wheel would be just a tensor product A1 times A2 times A3 times A4 5 times A6. And if we consider the map, which such that these 3 points go to this one, and the rest just goes. So this is 1, 2, 3, 4, and the rest is an isomorphism. Then this goes to simply the multiplication of these 3 elements times the rest of them. So this explains what to do if the map is surjective. But if the map is not surjective on points, so some points in the image are omitted, then, and I need one condition which I forgot here, so this is an algebra with unit. Then we just plug unity here, just plug 1. Okay, so since the algebra is associative, so things like this are well defined. The algebra is not commutative, but you might notice immediately that for any point we have a natural order on the preimage. So we know in which order to multiply things. So there is this functor. And then the definition is that the cyclic homology of A is just the homology of this category lambda with coefficients and then functor A hash. This is sort of a very nice way to package the previous definitions which Kohn also introduced into one line. Of course, to see that this has any relation, say, to Hochschild homology and some other, and well, any natural structure, one has to do some work. And let me just show you how the periodicity homomorphism comes about in this setting. So this is homology with coefficients. And as usual, we can consider the cohomology with constant coefficients. So coefficients in K, where K is just a constant functor. And then, so this is a lemma, which I'm not going to prove, but anyway. So this is just a polynomial algebra on one variable u of degree 2. For the proof of this, and also for much more detail about these things, by the way, you can consult Laday's book. I think it's called just cyclic homology. And it's rather a long book with very many details about these things. Huh? Homology are divided of the factorial, or the Schwick one, yeah. Just as in the group case. In the group case, homology is the derived of the coinvariance. So now, as usual in all this homological type formalism, just by stupid reasons, by adjunction, for anything, for any functor and the homology of coefficients in this functor, the cohomology acts on the homology. So, and this action is the exactly the periodicity map. So this is a module over this algebra. So there is a endomorphism of degree 2, minus 2. Yeah. Yeah. Or rather, like this. And then what Kohn proved is that the cone of this map is just the Hochschild homology of A. I think shifted by 1. So this will be my definition of the cyclic homology. Okay. And now I need a map like that. So to obtain it, I will need to introduce another small category related to that one. Namely, so we have category lambda, and I want to define some subcategory, lambda p inside. So objects of lambda are sort of these wheels. Now I consider objects of the form Pn, where n is some integer and p is our characteristic, and also this p. So I consider wheels with Pn marked points. And then there is a natural automorphism of order p. Just cyclic rotation. So my lambda p by definition has these objects, and the maps are those maps here which commute with this sigma. So objects, p is just the set of all Pn. And morphisms are morphisms of lambda which commute with sigma. Sigma. So this is a subcategory here, not a full one, by the way, just a subcategory. But now there is another relation between them. So conversely, you can, given a wheel with an automorphism, you can take the quotient. And this is a wheel of order n. So we have an embedding here, embedding of small categories. But we also have a projection. This I will denote by pi. So we have this category lambda, we have this subcategory, which can be in turn mapped into lambda. So this in fact, maybe let me change the notation slightly. So let me number objects here also by integers, but then this embedding will multiply the number by p, and the projection will keep it the same. All right, now one checks, and this is kind of surprising, but still true, that this lemma here also holds with lambda replaced by lambda p. And also this statement is also true for lambda replaced by lambda p. In fact, up to this point, everything is completely independent of characteristic, and it's true even over z. And this p doesn't even have to be a prime number, just any integer would do. And here, in all cases, we get homology. OK, so now proposition 1, which is also, by the way, independent of characteristic, is the following. For any cyclic vector space or a functor from lambda to vector spaces, we can compare two things. First of all, we can take just homology of lambda with coefficients in E. On the other hand, we can take E restricted to lambda p by means of this embedding, and then compute the homology of lambda p. And there is a natural map. This natural map, I don't want to go into details. It's easier to understand it yourself, but this is just by stupid adjunction reason. What's completely non-obvious at first is that this map is actually an isomorphism for any E here. This is known in topology as a cyclic subdivision lemma or something like that. The proof is slightly technical, but not so very difficult. And you can find it in my paper. This is written down. So if I want to compute cyclic homology of something, I might as well restrict to this lambda p for any p. So this is sort of one half of the ingredients I need for the Cartier map. And the other half, now I have to look at the projection p there, instead of the embedding. So this was true for any cyclic object, in particular for this special thing called a hash. Say it again? No, not at all. First of all, the objects are different. There is more objects here. Pi p, no, again not. The objects are the same, but there are more morphisms, because every morphism here has this automorphism of order p, this sigma. When we go downstairs, this becomes trivial. So this is, in a sense, roughly speaking, this is a semi-direct product of this category with just the group Z mod pz. This is roughly speaking. Honestly, it's not even a semi-direct product, but there is some kind of non-trivial extension. which you can formalize, but I won't need this, so I don't do this. So one can recover this by sort of from this projection. But it's easier to think of it as a subcategory here by means of this embedding. Okay, so proposition 2. It's not, proposition 2, I think, is not true for any cyclic object. One can write down some linear algebraic conditions, but I don't really want to do this because I will only need this particular one anyway. And proposition 2 says what we obtain if we take our object A hash and pull it, sorry, just homology, and pull it back by means of the projection. And the answer is that this is just Hochschild homology of A iterated many times. Let me sort of try to, I don't really want to give a complete proof of it, but just sketch. Projection P is actually a very, very good functor. I mean, in category theory, there is a notion of fibered category. This is an example of that. It's actually both fibered and co-fibered. It's very good. And particularly, it behaves almost as a very good map of topological spaces. So there are all sorts of base change formula and projection formula and so on. In particular, this is a projection formula. So what do we do here? We take something, pull it upstairs, and then project to just to the point. So equivalently, we can pull it upstairs, then project downstairs, and then project to the point. So this thing here is sort of tautologically, is tautologically isomorphic to the homology of lambda with coefficients in so we take the derived functor of the projection and then apply it to the same thing. And this one can compute by the projection formula because so we go up and then down. So this is isomorphic to just A hash times, in the sense of a natural pointwise tensor product, times the same procedure applied just to the constant functor. So essentially, all you have to do to prove such a thing is to analyze this complex of functors and what it does after tensoring. This is kind of a technical thing. I don't really want to do this, so using this. I want to use the claim. Basically, after you take this and tensor it with A, the resulting thing already splits into explicit sum of complexes. And for every such complex, you can show that cyclic homology of coefficients of this complex is the same as just Hochschild homology of A. And the relation is basically by this long exact sequence. And I repeat, the important thing is that this A hash here is not so very important. It can be taken out of the equation because of the projection formula. Okay, so I have those two functors and I have an equality like this, and I have an equality like that. So this is more or less the left-hand side of the Cartier map which I have to construct. And that there is a right-hand side. And now I can represent both as homology of the same category with different coefficients. So if I want a map from one to the other, natural thing to do is construct a map of coefficients. So what I need from pi upper star p of a hash to a p upper star of a hash. So let's evaluate this and some object. So these are functors from lambda p to vector spaces. Let's just take some object in lambda p and compute these functors at this object. So take some n. Then this evaluated at n, by definition, is just a to the power n, tensor power n. Now this evaluated at n. So how do we compute this? I mean, this is a restriction with respect to this map. So this is the same as a hash evaluated at ip applied to n, and this is just pn. So here we get a to the power pn. If I denote this by v, then this is just v to the power of p. So essentially what I need a map from vector space v to its pth power. Surprisingly, the rest just boils down to look at this situation. So once I find a map like this which is sufficiently functorial, the generalization to functors becomes immediate. We just take this map and then just notice that it's compatible with all the cyclic structure and so on. And we immediately obtain a map like this. So from now on, I will concentrate on this pure linear algebraic problem. And the generalization to cyclic object becomes totally automatic. But this linear algebraic problem is not trivial because, well, there is a very nice and completely canonical functorial map from the left-hand side to the right-hand side. Namely, the map which takes a vector and sends it to its pth tensor power. So there is a map from v tensor p, which sends a vector v to v tensor, so on, tensor v. This is completely functorial, canonical, but of course it's not additive. I noticed that this actually becomes additive if we do one thing. So the cyclic group of p elements acts here naturally, but just by transposition. And and it acts here just trivially. So we can consider the cohomology of the cyclic group with these coefficients. And the cohomology of the cyclic group is, of course, a very well-known thing. One can compute it by a standard complex, standard periodic complex. So a map like this, although it's not additive, can be used to induce some kind of map here. And the claim is that, so this is a lemma. The lemma says that this is an isomorphism for any I greater than 1, greater or equal to 1. Of course, here we have nothing. I mean, the cohomology of the group, of the cyclic group with constant coefficient is very simple, just a one-dimensional space in every degree. So this is basically just V in any degree. And I claim that if we compute the cohomology of the cyclic group with these non-trivial coefficients, then again we get V. And so the proof, so we have a map, we have to show that this is an isomorphism. In other words, we have to show that both things are the same size. Let's choose a basis in V. So let's think that V is just the vector space of functions on some finite set S. Then this pth tensor power is the set of functions on the pth power of S. And cyclic group acts through its action on SP. And now, since this is a cyclic group of a prime order, there are only two types of orbits which we have here. There are fixed points, and there are the three orbits. So this actually decomposes into functions on the diagonal plus functions on the complement to the diagonal. But here the action is free, so the representation is free, so there is no homology. So this vanishes. This has no homology. And this is, of course, just free. Now, this identification of this and this, which I given here, is not canonical. It depends on the choice of the basis. But since we already have a map, we can show that this map is good. So what we would like to do, we'd like to kind of correct this map so that it becomes additive, but still induces the isomorphism on homology. And hopefully also functorial. So ideally, we want, let me denote this by some letter n or rho. To correct rho so that it is additive functorial in V and still induces an isomorphism on homology. Of course, this is sort of what this would give us our map immediately. It's not possible to do this. And this is where algebraic topology comes in. So this is not possible. And it's not surprising that it's not possible, because if it were possible, then I would get my Cartier isomorphism without adding this strange topological ST type of thing. And so now let me try to do what I can with this. And in the end, what I will get would be a map from ST of V to some modification of this tensor power. OK. Now I need to remind you some things about algebraic topology. So it's kind of a digression, just for a moment. I need to remind you some very general thing, and then we'll apply it to that problem. So digression on Eilenberg-MacLane spaces. So I remind you that if I have some group H, let's say a billion group, and some integer n, non-negative integer n, then an Eilenberg-MacLane space KHN is by definition a topological space such that for any topological space we have homotopy groups. So we want the nth homotopy group of this thing to be equal to H, and all the other homotopy groups must vanish. It's a rather standard theorem which says that such a thing exists, and it's unique up to homotopy. So any two such things are homotopy equivalent. Most people probably saw space of this type with n equal to 1. So K H1. It's also sometimes called classifying space for the group H. And here, if n is equal to 1, this group needn't be abelian. You can take just any group, and there is a construction of this type. But if you want to go higher, then the group must be abelian. So we have these spaces, and if we fix the group H, and we consider Allenberg-MacLane space, okay, Hn plus 1, we can take its loop space, so the space of loops. In topology, all the spaces are supposed to be pointed, so there is a fixed point, and we consider the loops passing through this point. This is also a topological space, and this is some functor on the category of topological space as a fixed point. And taking the loop space shifts homology, so this must, by definition, be an Allenberg-MacLane space KHN. So these things for various n's are related by isomorphism of this, homotopy equivalence of this type. And one can also, so let's do it in stages. So one can also consider the homology of this Allenberg-MacLane space. So this is a topological space, we can take its homology. And then one shows that an equivalence of this type induces what is known as transgression map. So there is a functorial map from Hi, or rather just homology of KHN to so there is a shift of degree here. This maps to KHN plus 1. By the way, by Gurevich theorem, this thing has no homology in degree less than n. And in degree n, that's sort of a remark, in degree n, its homology is exactly the same as this unique non-trivial homotopy group, so this is H. And then this map is an isomorphism. This is in general, it's called a transgression map. So in degree n, it's an isomorphism, but then in higher degrees, it's highly non-trivial. I don't really want to reproduce. Well, there are several ways to define it, but you can look them up in any topology textbooks. Okay. Now, what I want to say now is that there is a very nice construction of the Allenberg-MacLane spaces invented, very nice sort of combinatorial construction invented by Dalden Puppe, I think. So there is a nice construction of KHN. Namely, we know that one of the ways to construct topological spaces is to start from simplicial sets. So I remind you that there is a finite category called delta, sort of the category of finite linearly ordered sets. Ordered sets. And by definition, a simplicial set is a functor from the opposite category to sets. These are called, objects here are called simplicial sets. And then there is a so-called geometric realization functor, which goes to topological spaces. Now, usually, I would say, well, in very, very many cases, this is pretty useless, because it's usually much easier to construct a topological space as a topological space rather than represent it as a realization of something explicitly simplicial. However, in this particular case, this works very, very nicely. Namely, I claim that an Eilenberg-MacLane space can be constructed as a topological realization, not only of a simplicial set, but actually of a simplicial abelian group. So if you consider functors from delta not just to sets, but to abelian groups, well, this is an abelian category. For any object here, we can take its topological realization. But the completely surprising fact is a theorem by Dold and Puppe. Dold and Puppe is that this category is actually equivalent to the category of complexes of abelian groups placed in non-positive degrees. This is strange because here an object is has enormous amount of data. So there are several abelian groups, but there are very, very phase and degeneracy maps between them. But it turns out that this all boils down to just a complex with a differential, nothing more. I mean, most people know that these things are somehow related and the derived categories are maybe related. But in fact, there is an equivalence for abelian categories, just on the nose. Actually, this thing has been used even in SGA, I think, several times. So it's not so completely esoteric, but still many algebraic geometers don't know this. So in any case, there's this equivalence. And this means that simplicial abelian groups are very, very easy to construct. We just take some complex, and voila. Here we get simplicial abelian group. And then a very simple lemma says that if we take, so let me denote this equivalence, or rather the inverse one, by dp. So Dold Puppe. So lemma, if we have some abelian group, we consider it as a complex, and we shift it downwards by n, apply this equivalence, get a simplicial abelian group, and get a topological realization. Then the claim is that this is exactly the Eilenberg-MacLane space. So the topological realization of this dp applied to H considered as a complex placed in degree n is Eilenberg-MacLane space KHN. And moreover, that transgression map, which I wrote there on the level of homology, also has a very explicit simplicial interpretation. So if one has some simplicial set, then to compute this homology, it's very well known what to do. So you have some simplicial set. Then to compute this homology, you do the following. You just consider the free abelian group generated by X, which is now a simplicial abelian group. And then if you take the corresponding complex, corresponding, for instance, in the sense of this equivalence, then this complex computes you the homology of X. So for simplicial sets, passing to homology is essentially just amounts to taking the free abelian group generated by our set. Let me put square bracket here. I think it's slightly better. So if we want to look at the homology of Eilenberg-MacLane space, what we have to do is we take H of shifted by n, we apply dp, and then we generate everything by this. And I claim that there is a map. So how should I put it? Okay, so this is homology, but then there is also a shift. So allow me some abuse of notation. I will just take the shift natural for complexes and just transpose it here without writing one more dp here, because otherwise we get horribly confused. And the claim is that this maps into k of dp. dp of h of n plus 1. I think, sorry, the shift is by 1 here. Yeah, so that is not like this. Or you can move the shift here, changing the sign. Or in fact, one can generalize. So this is a statement essentially about a complex of this type, some group placed in some degree. But this, I mean, the same construction also gives you this map for arbitrary complex here. So we can put some v prime here. And then here we have v prime shifted downwards. So there is this transgression map. And in this form, it's very obvious that you can iterate the construction. So you apply it to this one and so on, to this guy and so on. So let me do it correctly. Okay. And eventually you can pass to the limit. And this limit is what I want to denote by ST. So definition. For any complex well, or abelian groups or vector spaces or whatever. Let's say vector spaces. We define ST of V. So this is transgression. Let me note this by TR. I want to take direct limit with respect to these transgression maps. From K of I drop this dp. I mean, the notation is horrible as it is. So I mean, dropping this would not probably make it worse. Minus L. So we take the complex, we take the simplicial, we shift it downwards by L, take the simplicial abelian groups, take its homology, and then shift it back upwards. So what is immediately obvious is that this thing is not trivial because the transgression map in this degree, first degree where the things are non-trivial is just an isomorphism. So, there should be a dp here, then the inverse dp. Let me just drop it from notation, okay? Because so I take a complex, I shift it, I apply dp, I take this, and then I go back. So correct notation would be like this. Yeah, I think this is completely correct. Right. So I mean, this is defined for any complex, but just take a vector space placed in degree 0. So if V is just a vector space in degree 0, then we know that ST0 of V is isomorphic to V. But even in degree 1, this is already very, very large. This is some kind of limit of iterated tensor powers of V. This is something completely horrible. But what's important is that the homology of this thing is rather nice. So fact is that homology of this horrible complex is additive in V, linear in V. And in fact, it is non-canonically, well, yeah, non-canonically, maybe sort of canonically isomorphic to I mean, the whole complex is very non-trivial, but it's not possible to split it into sum of its homology functorially in V. This is really a non-trivial functor in V, which you cannot decompose into simpler pieces. But if we just look at homology, then this one can compute, and this is just so the ith homology is just isomorphic to the ith homology of this ST of K times V. So the homology is the same as if we just take V and multiply it by some fixed vector space. And this is a fixed thing which you have to compute once, and this is in fact what is known as dual to the Steenrod algebra. Ah? This one? This one? This is interesting. Should be 0. Sorry, I mean, no, this was. So when you have, for instance, a differential graded algebra, associative algebra, you can treat it as a functor from complexes to the category of complexes to itself, which is just multiplication by this differential graded Lie algebra. Here we have a slightly more complicated thing. We have a functor which is in general not even additive. It's a horrible functor. But on the level of homology, it's exactly as if it were a multiplication. Okay, so this is our ST. But it turns out that the fact of this being non-additive is not so important. What is much more important is that this is completely functorial. So now we can apply it to our non-additive map. Let's see what we get. So we have a map from V to tensor P, which is not additive. If I want to make it additive, this is just a map of sets, just my standard map rho. If I want to make it additive, I can do a stupid thing. I can just replace V with a free abelian group generated by V. Then this is an additive map. But of course, this K of V is very far from V itself. However, this map rho, as I said, is totally functorial. So I can play this game. And I can shift the whole thing by L. And then I, absolutely for free, get a map from this to V10 shifted by L to the power of P. Now I want to go to the limit, so I better shift upwards. This I also can do. So I have a map like this for any L. And now let's pass to the limit. And when I pass to the limit, on the left-hand side, I get exactly my ST of V. And now I have to compute what I get on the right-hand side. Well, let's see. First of all, this, unlike this, so here I take this completely non-additive operation of replacing something with functions on this considered as a set. Here I do nothing of the sort. So here I can just as well remove V outside of the bracket. So this is equivalent to V tensor P times K of L to the power of P minus L. Now here the notation is somewhat confusing already. Because I mean here I really should pass to simplicial abelian groups. And this very nice equivalence of Dolly and Puppe is not compatible with tensor products. So there is a standard tensor products on complexes where just usual Leibniz rule gives you the differential. And there is also very natural tensor products on simplicial abelian groups, just pointwise. And the functor is not quite compatible with these tensor products. However, what is true is that it becomes compatible if you don't care about the action of the permutation group and only care about homology. So this thing is this is a complex. So it's quasi-isomorphic to just the same thing computed, but with respect to the usual tensor product on complexes. And this is obvious what this is. So we take car placed in degree L. When we raise it to the power of p, it's just the same k, placed in degree LP, and then we shift it upwards. So this is quasi-isomorphic to k minus L p times 1 minus L, I think, yeah. Quasi-isomorphic. This is a huge complex, but it's acyclic in all degrees except for this one. And now when we pass to the limit, this goes to infinity, and the whole thing becomes just acyclic. So this maps into e to the power of p times some complex, let me denote it by p dot, which is acyclic. So on the surface of it, I lost everything. I mean, I want to work with homological algebra, so what uses the acyclic complex? I mean, it has no cohomology, right? However, what is important is that this map is actually also invariant with respect to the cyclic group. And so these guys have an action of the cyclic group also. And this is a map which is equivariant with respect to the cyclic group. I mean, here a cyclic group acts trivially. Here we have some action. So we really should think of this as a complex not just of vector spaces, but of representations of the cyclic group. And now an easy computation shows that this p here is like this. P0 is just identically k, the trivial representation. And all the other things are free representations of the cyclic group. I leave it as an exercise, or you can look it up in the paper. I mean, this is essentially a combinatorial exercise. Because, I mean, this P, it has an explicit basis, so you just look at the basis and see that the action has no fixed primes. So these are free modules. And now the conclusion is that if I take the cohomology of the cyclic group with coefficients in both parts, here, of course, the action is trivial, so I just get the cohomology of the cyclic group with constant coefficients times whatever I had. But what I get here is not trivial, and conversely, it's what is known as the Tate homology of the cyclic group. So I remind you that there is this very beautiful theory of Tate homology for groups, which uses the following fact, that if you have a finite group, then typically the category of representation of this finite group over some field of positive characteristic has infinite homological dimension. And so even if you have a complex which is acyclic, but which is infinite, say in one direction, this cohomology need not be trivial. And in fact, for the cyclic group, it's very easy to compute what this is. It is known. And this is just the usual homology. So the usual homology with some coefficients is a module over homology of constant coefficients. And here, the homology of a cyclic group of order P with coefficients characteristic P is periodic. There is a periodicity endomorphism of degree 2. So in order to get Tate homology, we just have to invert this. So this is usual homology with Tate, this periodicity homomorphism inverted. And I must note that we might as well invert it here, because I mean this is a map of modules over this thing. This is a free module, so since here U is inverted, this canonically extends to, should erase something. This we can embed into sort of the same thing. with U inverted times ST. And then this map extends here. So the upshot is that for any vector space V, we obtain, I mean, I'm basically just going to rewrite this thing, but let me do it in the middle of blackboard. So we have a map from this times the homology Z mod P Z, coefficients in K, to rate homology of Z mod Pz of coefficients in the tensor power. And this map is induced by a canonical map from ST of V to this tensor power times this acyclic complex P. This is our Cartier map. So this is just for a vector space. And to get a Cartier map, we have to apply it to these two things which I explained in the beginning. And as I said, if you evaluate on any object in the category lambda p, then this is a situation of this type. And it's an easy exercise to see that everything is compatible with the maps between different objects in lambda p. So we get a map from ST of this to this. Then we can use projection downwards and look at the induced, so this times P, sorry, homology, right? And then this gives you the periodic cyclic homology. Periodic because we have to have this localization here. So this localization in the finite computation comes out as a fact that we obtain a periodic cyclic homology, not just usual cyclic homology. But then by restriction, you can also get a map on the level of usual cyclic homology. Okay, so this is the construction. I think, yeah, that's all I want to say today. But being the last speaker, I have the honor of suggesting that we honor the organizers of the whole thing, because this has been a very long and successful school. I think people are very tired and satisfied. I have been there here only 1 week, and not all 4 of them, but still I'm very tired but satisfied. But you can imagine how hard it was for the organizers. And I think they did a fantastic job, and I think we should thank them. Just all hearts.